Alright, so in the previous lecture, we proved the Gratoskis theorem for simple three-connected graphs. Yes, so when you have a simple three-connected graph without having a K5 or K33 topological minor, then it has a convex drawing, convex embedding on the plane, so that every inner face is as convex, the complement of outer face is convex, and all the edges are straight line segments. Now we're not going to use the convex embedding for the rest of the proof. We need to prove Gratoskis theorem, right? So proof of Gratoskis theorem. How do we prove that, right? Of course, we only need to prove the backward direction, because forward direction is trivial. If you have a planar graph, all its topological minors are planar. Right. So let's use induction on something. Induction on, let's leave it as a blank. So if the number of vertices is small, let's say almost 4, then we know everything is planar. Right? Everything is just by drawing them on the plane, we can check easily that everything is planar. So I can assume that I have at least 5 vertices. How about simple? Why? Because otherwise, let's say I have a parallel edges, I delete the parallel edge and then apply induction hypothesis. So I want to apply induction, so let's do the induction on number of edges. And if I have a parallel edges, I delete it, apply induction, I still have no topological minor isomorphic to K5 or K33, so we have a planar graph, we have a planar embedding, and then along with this edge, you can add a parallel edge, right? What about loops? Well, we can always draw loops, right? Delete the loop, find an embedding, and then add a loop. So you can always do that. So I can assume the graph is simple. And I can assume that G is connected. Why? Well, if graph is not connected, then we apply inductions to each component, right? Okay, now here I need to use number of vertices as well, because I might have a component with a single vertex only, and with no edges, then, right, if I have a isolated vertex, then I cannot apply induction hypothesis over here if I said induction on number of edges, because number of edges didn't decrease. Now by adding number of vertices as a parameter, I know for sure that this thing will be definitely smaller than the original graph. Right, so if graph is connected, then I apply induction hypothesis to each component. No, not connected. Apply induction hypothesis to every component, and we get the planar drawing, planar embedding of each component, and just draw them separately. And I can assume the graph is 2 connected. Why? If I have an embedding, if I have a cup vertex, what do? We apply induction to everything, right? So if I have things like this, I apply induction over here. So I take out one component, so that's first graph, and then take out another component, and that's, rest of the components, right? So this is C1, and then this is C1 plus V, and G minus VC1. Now, both graphs are definitely smaller than our original graph in terms of the sum of number of edges and number of vertices. Now, by the induction hypothesis, this will have a planar embedding, this will have a planar embedding. And if in both embedding, if this vertex is on the infinite phase, then it's easy, you can draw that, but maybe it's not the case. But by using stereographic projections, and first embed on the sphere, right? So this cup vertex may be in some, this could be the cup vertex, right? Now, by you drawing it on the sphere and rotate the sphere so that you can put the North Pole in the face where V is, okay? And then apply stereographic projections. Then you end up with a new embedding where V is on the infinite phase. Now, once V is on the infinite phase, you can shrink the picture, and you can make sure that all the pictures of the first graph is sitting inside these black regions. Now you shrink it again and again and again, make it smaller, tiny, and then in the second figure, here is a V, right? No, maybe you have a graph, you find somewhere vertex V, and then you take this, copy it somewhere in a tiny region, right? So that's gonna be your embedding for the new graph. All right, so that's why we can assume the graph is two connected. And I can assume the graph has no vertex of degree 2. Why? If I have a vertex of degree 2, then just smoother, right? So this is sometimes called smoothing. And then this graph doesn't have a K5 or K3 topological minor, and therefore it has a planar embedding, and what you do is just to add one vertex in the middle of the edge, right? Now, we may also assume that G has no, okay, G is reconnected. Why? If not, we already said the graph is two connected. So if not, you have a vertex cutoff size 2, right? And what we do is you take one component after deleting x, and then the rest of the graph is here. You apply induction to this graph. And I don't know whether these two vertices are the JSON or not, but this is going to be my first graph. So let's say G1. And then G2 is my second graph. Okay. Now, I claim that this is actually a topological minor of G. Both G1 and G2 are topological minors of G. Why? Because first of all, graph is two connected. So that means the cup vertices of this in set X, these vertices will have neighbors in every component in G delete X. So this component will have neighbors of this guy and neighbors of that guy. Then you can find the paths. So I can always find the paths joining these two neighbors. And there may be many neighbors on this side, but if I pick one side, I can also find paths joining these two vertices in the cut set. Now, if I take this blue path over here and smooth vertices of degree 2, then with degree f is this guy. So this is a topological minor of this graph G. And how about this? I take this red path and smooth it, right? So that's my G2. So both G1 and G2 are topological minors of G. So G1, G2 are planar by induction. Is this true? Yeah, I mean, number of vertices has been reduced, so I can apply induction. Now again, now we have the same situations. Let's say I have embedding of G1. So let's say this is my G1 planar embedding, and this is the red edge. Okay. Now what we do is we again draw in a different way so that this red edge is on the infinite face. Can you draw that? By drawing it on a sphere and then rotate it and pick the North Pole around this red edge and apply stereographic projection again, then this red edge will be on the infinite face. Now I'm gonna draw it in a weird way. Just stretch this red edge far away, and then all the other things will be stretched as well. Thus this is my new drawing of the same graph. Okay, there's so extra edge. Yeah. All right, so I can draw basically like this way in a tiny way, right? So everything is around these small regions. And in my second graph, so I find the planar embedding of the second graph and then find the blue edge. Blue or red? Okay, red edge. And then replace this red edge with this guy, right? Is that good? Yeah, that's fine. Yeah. So that's how we draw it. So now, thus G is simple, reconnected, and then we are done because we knew the theorem is true. Right. So this proves the Gratoskis theorem. Gratoskis is a Polish mathematician. So once I gave exam problems on, using Gratoskis theorem, some students didn't remember Gratoskis, and so it was by some Russian mathematician this theorem is true. But actually, Gratoskis is not Russian; it's a Polish mathematician. All right. Now, here's some corollaries of corollary. This is commonly called Wagner's theorem. Which says that G is a planar. A graph is planar if and only if G has no, instead of topological minor, you can say minor isomorphic to K5 or K33. I might have mentioned it, but maybe this could be a good homework problem. Okay. All right. So instead of topological minor, you can say in terms of K, in terms of minor, and still it gives you two exactly same graphs. Now, some of you may wonder what happens if you go over the plane. What about torus? Or what about projective space, projective plane, etc.? So here are some of the theorems, right? So what is projective plane? Okay, I mean, let me throw it this way, maybe. So you identify opposite things. If you took the topology course, you may know what it is. So this point is identified with that corner, right? So if I have a projective plane, I can draw K5, for instance, Y. Let's see. How do I draw K5? So okay. So for 5 vertices, I need to draw 2 edges. If I go out this way, I arrive here. If I go out this way, because the surfaces are put together, right? So going out this way will arrive this way, and there's no crossings. So this is embedding of K5 on a projective plane. Okay, I mean, you can do more than that. I should have done better drawing. Yes, for instance, let's delete this edge. Right? Can I have a K6? Is it possible to have K6? I put a vertex here at the corner. All 4 vertices is actually same vertex. Right? These are all same vertices, and let me see if it does it work. Maybe I'm failing again. Right, so this red vertex, new red vertex, the corner vertex is adjacent to all existing 5 vertices. How about the last edge? I didn't draw the edge from this vertex to that vertex. Well, now I can go like this way and then get out here, right? So this way, 6 vertices are drawn on the projective plane and no 2 crosses. That's right. So this is embedding of K6. So if you go to a higher genus surface, you can embed more graphs. And then you may wonder what kind of graphs you can embed. And you can wonder whether you can actually characterize that. And there's an analog of Gratoskis theorem. So for instance, here's a theorem. There are 103 graphs. I won't tell you what they are, such that G can be embedded on a projective plane if and only if G has no topological minor isomorphic to H1 up to H103. Okay, and this 103 is type number. Exactly, and this has been completely characterized. You can also talk about minors. And here's another theorem that there are exactly 35 graphs. G1 up to G35 such that G can be embedded on a projected plane if and only if G has no minor. Isomorphic to G1 up to G35. And even for torus, there is such a theorem saying that there are only finitely many such exceptions, such forbidden minors. However, it doesn't say, I mean, nobody knows the complete list of them. There are more than 1,000 graphs. Some people did the computation by computers, and there are more than thousands. So far, we were not able to completely characterize all the forbidden minors for characterizing graphs embeddable on a torus. And yet, here's a theorem. It's also a consequence of Robertson and Seymour. And there is a direct proof, but it says that for every surface S, there exists a finite list, let's say a list of graphs G1 up to GK, such that G has an embedding on S if and only if G has no minor isomorphic to any of G1 up to GK. All right, so that's surprising result. So it's not a coincidence that the planar graph has exactly two forbidden minors, K5 and K33. What I find it striking is that you never need an infinite number of forbidden minors. You only need finitely many, and that's because of inherent structure of minors. Okay, so that's about it. So we covered the Gratoskis theorem. Now we go to dual graphs. No, I didn't write today. So lecture 13. Second part. Dual graphs. Planar graphs have really nice property called the dual graphs. So if you have a house, and what is dual, I pick a vertex in each face, and 1, 2, 3, 4, 5. So that's a dual. And this is called the geometric dual. And typically we write G star. So let me define precisely for a graph G. For a plane graph G, because we want to fix embedding, the geometric dual G star of G is a plane graph H such that oops, every face of G has precisely one vertex of H, and if E is an edge I need a bijection, so let's say there is a bijection, let's call it star, from EG to E of H such that if E is an edge of G, then H has an edge the edge E star of H crosses E exactly once and joining two vertices of let me not say that, E exactly once and no other edges of H cross E. Right, so that's the definition of the dual graph, right? So let's see what in this example, right? So for every edge, there is exactly one corresponding edge which crosses this, and no other red edges cross this edge. So that's the definition of geometric dual. Now, depending on the embedding, you might have a different dual graph, right? So remember, you have a same planar graph, we're having two different embedding, and the dual graph may be different. So that's why we have to fix the embedding. So that's why we say plane graph instead of planar graph. Here's observations. If H is the geometric dual of G of a plane graph G, then H is connected. Why? Because pick two vertices VW of H. Now in the initial graph they are in a different phase, right? Now let's think of the plane minus all the point sets of the vertices. This is connected, right? Topologically. Because you take a plane, you delete some finitely many points, you still have a connected set of points, right? So that means between any set of points you have a curve. So I can find the curve connecting these 2 points on the plane. Now this curve will go through, will cross some edges. It could be the same edge twice. Now what does that mean? That means I had so if I cross one edge, E of graph G, then I use E star, right? So pick a curve connecting VW in plane minus V of these points, and then this curve crosses edges of G, E1, E2, EK in this order, then E1 star, E2 star. So this is a sequence of edges of H inducing a walk from V to W. So H has a path from V to W. Right? So whenever you take a geometric dual, you have a connected graph. Now, that's one property that prevents something like this. When eventually when you say something is dual, then usually we want to have the property that dual of dual is itself, right? So we want to say that geometric dual of geometric dual is itself. Now, if graph G is disconnected, you cannot say that, because the geometric dual of plane graph is always connected, and then geometric dual of that is always connected. So we will never go back to the disconnected graphs. But like still, we can prove that something like this if H is the geometric dual of plane graph G, and G is connected, then G is the geometric dual of H, right? So when you have two graphs, if H is the geometric dual of plane graph G and G is connected, then G is also the geometric dual of H. That's why we call it a dual. So how do we prove that? So by the Euler's formula, the number of vertices minus number of edges plus number of faces of G is 2, because graph is connected. Okay? And similarly, number of vertices of H minus number of edges of H plus number of faces of H is 2, because H is connected. But remember that each face of G has precisely one vertex of H. So the since number of faces of G is equal to number of vertices of H, we deduce that number of vertices of G is equal to number of faces of H. Alright? So potentially now, right, now the number of faces of H is equal to number of vertices, and we need to prove the first property of the definitions. So if F is a face, okay, let's say F is a face of H, right? So if I have a face, does it contain a vertex of G? Then there is an edge E star on the base boundary. On the base boundary, I can find an edge E star. Wait, am I cheating a little bit? Why do I have a face boundary? Well, am I assuming that every face has a face boundary? Well, what can happen? Like, what happens if graph has no edges? If G has no edges, then H has no edges, and then G will, again, that's trivial, right? So I should add a warning mark. We may assume set of edges is not empty, right? Otherwise, you may have you cannot choose E star. All right, so there's an edge on the face boundary. Now pick E. Then E crosses E star, and E crosses no other edges of H by the definition 2, right? So here is the E. Now what does that mean? This means one end of E is in F and another, okay, I don't care the another end. That means F has at least one vertex. This proves 1 for G, right? In order to say that graph G is a geometric dual of H, I need to prove that every face of H contains at least one vertex of G. And this shows that this face F contains at least one vertex. Now, by counting argument, we knew that number of faces of H is equal to the number of vertices of G, so therefore no face contains two vertices. Thus, the first property holds. And second property is automatic. It's because second property itself is symmetric. So this proves that G is a geometric dual of H. All right. Now, here's an interesting attempt. So far, whenever we talk about geometric dual, we have to have embedding. Now, can we extend this concept of geometric dual to more general class of graphs where we don't talk about embeddings at all? So that's what we mean by this thing. So this thing called abstract dual. So now we're not going to talk about planar graphs. We just say that G and H be graphs. And then we say H is an abstract dual of G if there is a bijection star from set of edges of from G to set of edges of H such that F is an edge set of a cycle of G if and only if f star, which is the set of edges corresponding to f, is a minimal non-empty edge cut of H. Okay. What is a minimal non-empty edge cut? What is an edge cut? All right. F is an edge cut if G delete F. F is subset of edges. Okay, edge cut of H if F is subset of edges, so that G edge H delete F has more component than H. Then we say F is an edge cut. All right. So this is the definition of abstract dual. Now, why do we care? Why do we care about? Okay. By the way, what is a minimal non-empty edge cut? It's a minimal set which has the property that is non-empty edge cut. Okay. Am I doing all right? Yeah, this is fine. It's a bit weird. Why do I say non-empty if I define edge cut like this? Oh, okay. So let me not define edge cut like this. Let me change the definition of edge cut. If F is set of edges for some X, which is non-empty, which is proper subset of G. So delta X is the set of edges having one end in X, another and in the complement, not in X. So what is edge cut for us? So it's gonna be like, you take a X complement, and so the set of edges in the middle is called the edge cut. And if I have a graph like this, then this set of edges is an edge cut, but not minimal. And this thing is minimal, non-empty edge cut. Okay? Now, why do we care? Because of this property. If H is the geometric dual of a plane graph G, then H is also an abstract dual. Note that I use the word "un" instead of "the" because the abstract dual is not unique. Why is not unique? If this proposition is true, then for the same planar graph, you have different embedding. You might have a different embeddings. Each different embedding will give you a different geometric dual. And if each different geometric dual will be an abstract dual. So the abstract dual is not unique. So that's why I'm not saying it's the abstract dual, I'm saying an abstract dual. Okay? Now, if I have a geometric dual, then I have abstract dual. Why is this the case? So we first claim one direction, if f is an edge set of a cycle in G, then f star contains a minimal non-empty edge cut of H. Why? Because imagine that I have a set of edges which forms an edge cut. Right? Oops, no. I'm kidding. Right. So this, let's say F is the set of edges in the cycle. Then there's no edge joining vertices inside to the vertices outside. So by Jordan curve theorem, F star is an edge cut. Right? Right, there are vertices outside and vertices, inside the vertices outside. There's no edge crossing it because F is a simple closed curve. So that's F is an edge cut. So F star contains a minimal. Whenever you have an edge cut which is non-empty, then it contains a minimal non-empty edge cut. Right? So this direction, it's easy. What about the other direction? If F, let's say F star is a non-empty edge cut of H, then F contains an edge cut of a cycle. Why? Proof. Suppose not. Then if F doesn't contain a cycle, then F forms a forest, an edge set of a forest. Right? If you have an edge set of forest, then when you delete it, you only have a one face. So a forest, any planar embedding of a forest has only one face. So that means what does that mean? That means there is a curve in R2 minus F. There is a curve connecting any two vertices of H. What does that mean? If I have a curve connecting two vertices of H, I can convert it to a walk. So that means H has between any two vertices of H, there is a walk. as a graph theoretic term, okay? Because if I have a curve connecting two vertices VW, and here are the edges crossing, edges of G, right? E1, E2, E3, and none of these edges are in F, right? None of these edges are in F. So if I have these edges, then E1 star, E2 star, EK star is a walk in H from V to W, where none of these stars are not in F. None of them are in F. What does that mean? That means any two vertices are joined by an edge not in F. So G delete F is connected. No, H delete F is connected. Right? Contradiction. Right? This contradicts the assumption that H is an edge cut. No, F star is an edge cut. All right. So now this is the end of proof. Why? Why is this end of proof? If I have a cycle, then it contains something which is an edge cut, and then it contains something which is a cycle. But no cycle contains another cycle properly, so these two are equal. All right, so that actually is a proof. Is it clear? Let's show you the definition again, right? We have to have a bijections between set of edges forming a cycle in G and then set of edges which is minimal non-empty edge cut. Now what I showed is that edge set of cycle contains, in the image, it contains a minimal non-empty edge cut. The minimal non-empty edge cut contains in the image edge set of cycle, but no cycle contains another cycle as a properly, so everything is same. So what you end up is bijections. All right. Now I want to show you two properties of abstract duals. So one property is that, okay, let's okay, minors and duals. So we can easily observe the following. If H is a geometric dual of G and E is an edge of G, so let G be a plane graph. Okay, then G delete E. If I have a G delete E, what is the geometric dual? When I delete an E, then these two faces are identified, right? So it's kind of contractions. Okay, so H contract E star is the geometric dual of G delete E. If H is the geometry, and furthermore, if I contract E, so it's contracted, then nothing changes except we lose one edge in the dual. So it's easy to observe that contractions correspond to deletion in the dual, deletion correspond to contraction in the geometric dual. Now, actually, we have the same thing. All right, so what do we have? If H is an abstract dual of G and E is not a roof of G, then H do I care? Okay. E is not a roof, so let's contract E. So H delete E star is an abstract dual. So that's the first property, and the second property, if H is an abstract dual of G and E is, and I don't care, then H contract E star is an abstract dual of G. And the proof is straightforward. I'm not gonna prove it. Maybe it's gonna be a homework. You can try. So another property is if H is an abstract dual of G, then G is an abstract dual of H. Again, it's nice exercise to study. And here we don't need the condition that G is connected. For geometric dual, we need the graph to be connected, but abstract dual may be disconnected, so it's okay. So far, when you look at the definition of abstract dual, this doesn't assume any planarity, and you may think that, we might have a generalization of the concept of geometric dual to non-planar graphs. And here's a theorem due to Whitney. Which says the following: a graph has an abstract dual if and only. What graphs have abstract dual? And of course, all planar graphs have abstract dual because geometric dual is an abstract dual. And it turns out the graph has abstract dual precisely when graph is a planar. Surprising, right? How do we prove? One direction is trivial. This direction is trivial. What about forward direction? If it's non-planar, I have a K5 and K33 minor, and by these two propositions, if we have a minor, if we have an abstract dual, then every minor has an abstract dual. So it's enough to show that neither K5 nor K33 has an abstract dual. All right, big Pythagoras theorem. Because if a graph is non-planar, then it must have a K5 or K33 minor. So here's the claim. if H is a connected abstract dual of a graph G, a connected then E is an edge set of a spanning tree of G if and only if its complement okay, let's see what happens. Something is an edge set of a spanning tree. What does that mean? That means it's a maximal edge set not containing any cycle. What that means is, in the complement, E H minus E is a minimal edge set meeting every cycle, right? It intersects every cycle. Now, when you go to the abstract dual, this becomes EG, okay? When you go to abstract dual, EG minus E star is a minimal edge set meaning all non-empty edge cuts. What does that mean? What are the minimal edge sets meeting all non-empty edge cuts? So that means is a minimal edge set forming a connected subgraph. Of H. So that means EF is an edge set of spanning tree. All right. So this claim is nice because now it says that when you have a spanning tree, then complement is an edge set of spanning tree in the abstract dual. Okay. All right. So what this claim is, right? So, I mean, we actually proved it while stating the claim, right? So what we proved is that if you have a connected abstract dual of a connected graph, then something is an edge set of spanning tree of graph G if and only if its complement is an edge set of spanning tree. So how are we going to use that? So let's look at the K5. Let's say, suppose K5 has an abstract dual H. Now K5 is connected, but abstract dual is not. Right? Why is this getting smaller? All right. So K5 is connected, but abstract dual is not connected. Now, what we do is, first of all, we may assume H is connected. Why? Because I only care about, like, if this is my H, then I will glue them together by picking one vertex in and then glue. And the set of non-empty edge cut doesn't change. right? This set was empty, but it has nothing to do with, right? It's an empty edge cut, so it's not gonna appear. So, right, H and H prime have the same set of non-empty edge cuts, so we can still say that H prime is an abstract dual of G. Now, that means if F is spanning tree of K5, I know that it has 4 edges. A spanning tree of H has 10 minus 4. 10 is number of edges of K5, it's 6 edges. Right? What about how many vertices do I have? 6 plus 1. If a spanning tree has 6 edges, then the graph has 7 vertices. Okay, so H has 7 vertices and 10 edges. So the average degree of H is 2 times 10 over 7, which is less than 3. So H has a vertex of degree most 2. So H has a minimal non-empty edge cut of size 1 or 2. That means K5 has a cycle of length 1 or 2. That's a contradiction. So that's why K5 doesn't have an abstract dual. How about K33? It's got how many edges do I have in a spanning tree? 5 edges in its spanning tree. So that means 9 minus 5 edges in the spanning tree of H. So that means 5 vertices in H and 9 edges in H. Then average degree of H is gonna be 2 times 5. No. 2 times 9 divided by 5. It's less than 4. So H has a vertex of degree at most 4. So H has a minimal non-empty. I mean, this, if you have a vertex V of degree at most 4, this set could be minimal non-empty edge cut, but maybe potentially a subset is a minimal non-empty edge cut. But anyway, it's a size at most 4, at most 3. So that means K33 has a cycle of length at most 3. Contradiction. Because K33 is K33 is bipartite. You don't have any triangle. Alright, so that proves the Witten's theorem. The graph has an abstract dual if and only if it's planar. So this is somewhat disappointing, right? Because initially we build the theory of abstract dual to extend the theory of geometric dual, but now this shows that you have nothing but planar graphs. Okay, so that's it. So that's the ending of the planar graphs. So in the next lecture we will talk about graph coloring.